Welcome to this explainer. Forcing incredibly thick, viscous plastics into microscopic mold cavities really shouldn't be physically possible, yet we do it every single day. Today, we're demystifying this engineering marvel. Our main focus here is to truly understand the properties and the specific factors that dictate the flow behavior of polymer solutions and molten polymers when they are in liquid form. Because once we grasp these underlying mechanics, we can finally understand how these materials actually behave when they are heated, pushed, and stressed during manufacturing.
Okay, let's dive into our roadmap for today. We're going to cover molecular mechanics of flow, temperature and molecular weight, shear thinning, melt fracture, suspensions, and finally, measuring polymer flow.
Section 1. Molecular mechanics of flow.
So, what actually holds a piece of plastic together when it comes to flow? You might think it's those strong, rigid carbon-to-carbon bonds, right? Well, actually, scratch that. For flow behavior, they're held together by much weaker intermolecular forces called van der Waals forces. And these forces weaken dramatically as the distance between the molecules increases. So when we apply heat, the molecules vibrate more, they push each other apart, and this creates what we call free volume. This free volume is literally the physical space that allows the molecules to move and slide past one another, which is what enables the material to flow on a macroscopic level. We can even trigger this chemically by sneaking plasticizers right between the molecules.
And this brilliantly illustrates what we're talking about. Think of a polyethylene molecule chain as basically a microscopic, highly tangled bowl of spaghetti. These long polymer chains, which often have thousands of repeating units, are completely entangled with one another. So, for a molten polymer to actually flow, thousands of these massive chains have to constantly slide past each other. They have to overcome that internal friction and those weak van der Waals forces. That requires energy, and that energy dictates the fundamental flow behavior we have to manage on the factory floor.
Section 2. Temperature and molecular weight.
Now, the number of repeating units in that chain, meaning its molecular weight, pretty much dictates everything about how the fluid is going to behave. Let's compare the extremes. If we take a polymer like polystyrene with a super low molecular weight, say a degree of polymerization of just 10, it's sticky, it's soft, and it flows incredibly easily at room temperature. But if we ramp that up to a degree of polymerization of 1,000, that exact same polymer turns into a stiff, highly viscous nightmare to push through a mold. It's a fundamental trade-off. Higher molecular weight gives you higher structural strength and resistance to defects, but you get hit with exponentially higher viscosity.
Now, what's really interesting about processing these materials is this very narrow processing region. It's nestled right between the glass transition phase and outright thermal degradation. To get the polymer to flow safely without completely ruining it, we have to push it precisely into this zone where it acts as a viscous liquid. It's a really delicate operation, carefully navigating that perilous space between a rigid solid state and just burning the material up.
To break this high-stakes balancing act down a bit further, the safe processing temperature usually sits about 45 to 100 Kelvin above the glass transition temperature, but as we just established, increasing molecular weight raises the viscosity, which pushes your required temperature even higher. Plus, time is a massive factor here. If you force the material through an extrusion die at a much faster rate, the molecules literally do not have the time to relax into their new shape. When you shrink that processing timescale, you shift the required processing temperature upward. But there is a hard ceiling to this whole game, which is the thermal degradation limit. If we get it too hot while trying to force it to flow, the polymer simply burns.
Section 3. Shear thinning and deformation.
So if we can't always just add more heat without ruining the plastic, how do we actually get it to flow faster into tight molds? Well, think back to that tangled ball of spaghetti. In a low shear state, our polymer chains are just a tangled mess. But as we increase the shear rate, meaning we're literally pushing and dragging the fluid along a mold wall, those molecules physically align themselves into neat rows. And this alignment drastically reduces internal friction. It's the perfect explanation for shear thinning, which is also known as pseudoplasticity. Basically, the harder we push the polymer, the more the molecules align and the more the viscosity actively drops. It is an absolute game changer for manufacturing.
Section 4. Melt fracture and instability.
But there is definitely a hard limit to how hard we can push. When you push processing times to be shorter than the polymer's natural relaxation time, stresses just build up immensely. And this is exactly what happens when we try to cheat time. Once that shear stress hits a critical value, which is typically around 0.1 megapascals, the melt essentially fractures. The result? You get terrible visual defects like a shark skin texture, or even severe intermittent spiral separation, also known as spurt flow. The material basically loses contact with the inner die walls in this violent stick-slip effect, and it completely ruins the final product.
Section 5. Suspensions and viscoelasticity.
Up to this point, we've talked purely about raw polymers. We understand how the pure plastic behaves. But what actually happens to all this delicate molecular flow if we dump solid particles into the mix?
Because in the real world, polymers are almost always filled with solid particles like fibers, glass spheres, or flakes, usually to increase strength or conductivity. But adding these completely rewrites our flow dynamics. First off, particles inherently increase the overall viscosity of the fluid. Second, during flow, these particles bump into each other and cause cluster agglomeration, completely changing the internal structure. And finally, they introduce this fascinating phenomenon called thixotropy. This means that as you continuously shear the fluid, these clusters break down, causing an initial drop in viscosity over time until a final steady-state structure is formed. Understanding this is absolutely crucial, because if you don't account for how these clusters break apart over time, you're never going to get a uniform flow into the far corners of your mold.
Section 6. Measuring polymer flow. Let's move on and see how engineers actually measure all this chaotic behavior in the lab. To test these molten polymers and map out their properties, they use rotational rheometers, specifically Couette devices. Two of the most common are the cone and plate and the parallel discs. Now, both are fantastic because they only need a tiny sample size, like maybe 1 gram. Parallel discs are super handy because you can easily change the temperature without reloading your sample, but their major flaw is that the shear rate isn't uniform across the disc. So for complex, non-linear studies where we absolutely need precision and a uniform shear rate across the entire sample, we rely on the cone and plate.
When operating the cone and plate rheometer for highly viscous polymer melts, these instruments always operate in what we call the gap loading limit. This is a huge deal because it means the shear wave we generate propagates entirely across the gap without any damping. And by doing this, we can accurately measure the torque on the cone and its angular velocity. That gives us the exact mathematical data we need to map out the intricate flow behavior and all those viscosity curves we've been analyzing today.
So the crucial point we really need to take away is perfectly summarized by this quote. At any temperature, a polymer can be either a liquid or a solid, depending on the timescale or the speed at which its molecules are being deformed. Polymer flow isn't just about melting plastic, right? It's a constant, high-stakes battle against time and molecular entanglement, which leaves us with a pretty fascinating question to think about. If time alone dictates whether these materials act as solids or liquids, what other seemingly solid objects in your everyday life are actually just flowing on a timescale we simply cannot perceive? Thanks for joining this explainer.